Hi, this episode is direct sequel to the previous one. Therefore, we're gonna continue to examine crease orientation in the light of flat foldability rules. In this episode, we're gonna finally deal with examples that include so-called central flaps. Again, let's start from yet another simple example. This new example consists of 9 flaps symmetrically arranged on a paper. This model is simple, so I believe you should be able to define orientation of all axial and ridge creases. That's why we will skip this part. Now, we come to the real problem. Flat foldability. It is obvious that we have to add few additional creases in order to satisfy Miyakawa's and Kawasaki's theorem, since 5 vortexes do not satisfy them. Now, one tip from experience. Whenever you have one or more central flaps that do not satisfy flat foldability rules, it is wise to start with them. We should solve them first. So, let's start with central vortex. This vertex has 8 creases, 4 of which are mountains and 4 valleys. And of course this is a problem, since the difference between valleys and mountains is 0, not 2. What we've done in previous examples was adding additional creases, but that's not an option here, since we already have all 8 creases. There is no room for more. So, what is the solution? It is actually simple. However, in order to fully appreciate this approach, let's establish a few, I don't like to call them rules, but rather guidelines. You see, in principle polygons on paper edges should be free, meaning they should be allowed to rotate in any direction. But as far as central flaps are concerned, this is usually not the case. Most often central flaps need to be folded so that they are hidden in between adjacent axial lines. They should be almost interlocked inside some other flap or a river. It might seem complicated, but it only sounds so. To make this idea more understandable, I'll use our simple example and show you how to do it, how to hide the central flap. Let's start by folding the central flap first. Do you see which part of the paper the central flap occupies? This part should be folded first. You see, this is how it should look like. So, what we still need to do is to fold all the other flaps. This should not be that difficult, since all of them are on the paper edges. Okay, this is our base, completely folded now. As you can see, it resembles the stick figure. It consists of 1 central flap and 8 flaps on the edges. Before taking the next step, I'd like to draw your attention to the crease pattern once again. If you look closely, particularly at the creases that form the central flap, you can see that there is no hinge crease whatsoever. The central flap polygon is barely visible. That's because the central flap is, in relation to all the other flaps, pointing in the opposite direction. The central flap is pointing up, while all the other flaps are pointing down. Do not be mistaken, this is a perfectly legitimate crease pattern. The only problem comes from the fact that the central flap and consequently, the whole base, is too wide. It should be narrowed down. However, if we would do this simply by folding the whole base like this, we would get a narrower base, but most of the flaps, especially those on the paper edges, would be locked inside one another. And that's hardly ever useful. That's why we need to narrow the base down in such a way that will keep all the flaps on the edges free. We'll do this by hiding the central flap in between adjacent axial creases. This is the approach I was talking about a few minutes ago. Remember this, in reality central flaps are hardly ever free. But let me show you this on our simple example. What do we really want? We want to fold the central flap over its polygon edge, thus forming a hinge crease. Please, bear in mind that up until now the central flap had no hinge creases whatsoever. So what are we gonna achieve with that? Well, if you remember, when we simply folded a whole model over its central line, thus narrow it down, we got a central horizontal axial crease that was partly a mountain and partly a valley. But we didn't like it. Because such configuration was not useful at all. Now, if we fold the central flap like this, folding the central flap over its polygon edge, and then if we narrow the whole model down, the immediate consequence is partial reorientation of axial crease and, of course, formation of the hinge crease of a central flap. You see? Look at the crease pattern. Doing this, we've managed to press in the central flap in between axial creases of some other flap, actually hiding it inside that flap. Using this procedure, this simple idea, we'll get a base that is only 1 unit wide, as it's supposed to be. At the same time, all flaps on the paper edges will be free. Do you see these flaps? They can rotate in any direction. Only a trapped or a locked flap is the central one. One that is hidden inside one of the flaps on the paper edge. Just like we wanted. I hope this is clear. I hope you all understand the whole idea. It is very important that you do. So, let me repeat this idea once again. In most cases, I cannot say always, central flaps have to be reoriented in a way that will make them hidden in between axial creases of some other flap or a river. I hope you will remember this approach, this idea. You will use it very often. Now I'd like to show you an additional example. This one isn't particularly complex either. What is interesting about it is the fact that it contains more than one central flap. Do you see the circles? As you can see, we have 3 central flaps. Apart from that, everything else is more or less ordinary. There are no other special or distinctive features. We don't even have a river. Now, let's define the orientation of the basic creases. I'm sure that the procedure of defining the crease orientation has more or less become clear by now, so I'll skip this part again. Now, just like always, we've come across the problem of flat foldability. It is obvious that we need a few additional creases so that all vertexes would be able to satisfy Miyakawa's and Kawasaki's theorems. If we take a really good look, we'll realize that there's a substantial number of ill-defined vertexes. 14, to be more precise. But don't panic. To solve first 3, we only have to add additional hinge creases straight toward the paper edges. Now, what we are interested in here are these vertexes that represent the tips of central flaps. Can you see them? Do you see that, just like in the previous example, all 3 vertexes have 8 creases? And as you've probably guessed by now, 4 of the creases are mountains and 4 are valleys. Therefore our problem is a classical one, the one already explained in our previous example. So what's the solution? I'm sure you know it. I've already shown you how to deal with this kind of problem. But let me remind you. All what we have to do is to fold all 3 central flaps over their polygon edges, thus forming 3 additional hinge creases. Also, please be aware that 1 axial crease in every vortex is reoriented. Also, doing that, we solved the flat foldability problems in 6 adjacent vortexes too. Now, only what is left is to solve these 2 remaining vortexes in the middle. They are easy. Only what we have to do is to add additional hinge creases straight toward the paper edges. Doing that, please be aware that vortexes on the left and on the right must be rearranged too. Nothing complicated, but be aware of that. That is all. Now, what is left is to try to fold this model. Let's try it together, let's solve it step by step. Let's start. As you can see, we already pre-crease it. We did this only to ease the future folding since, as you know, a paper remembers. And now what? I hope you remember that the easiest way to fold such a model is to start with central flaps. Always start with central flaps. Always. Believe me. The first thing to do is to fold the paper over the line that connects all the central flaps. Can you see? Then one after the other, we have to press in these transverse creases in between the central flaps. You see? Do it slowly and the model will collapse just the way we wanted, exposing the central flaps. Now we have all 3 central flaps. 1, 2, 3. We also have 2 small additional flaps on the edges. So we can go one step further and fold the rest of the model. First, we should fold these 2 large flaps. It's relatively easy since we've already pre-creased them. Do you see how the paper remembered its previous creases and positions? By the way, this folding procedure where we divide 2 flaps is called Elias stretch. We can finally fold the last 3 small flaps now. What remains to be done is to hide these central flaps inside some other flaps in order to narrow the base down to 1 unit size, while at the same time freeing the flaps on paper edges so they can rotate freely in any direction. How exactly should that be done? That's what I'm gonna show you in the next episode. Nevertheless, if you want to, you can try to do it by yourself. You've learned all you need to know by now. The next episode shall also give you a more detailed insight into the problem of flat foldability and central flaps. In the meantime, take good care and see you in the next episode.